Hey everyone, this is Cassidy. Today we're going to be talking about equilibrium. So let's start off just with a basic definition. A chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. So what exactly does that mean? So let's get a really simple equation to practice with. We have our starting reactant here, and then we have our end product, right? We can see that our equation is balanced, so we're all good to analyze this. So technically, though, we have two reactions going on, right? We have our reactant turning into the product, but we also have the product turning back into the reactant, right? When you have an equation like this happening in a container, we can have it proceed in the forward direction or in the reverse direction as seen right here. So this is stating that an equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. So the speed at which this reaction is happening is the same exact thing as the speed as when this reaction is happening. So something that gets a little confusing is that some people think that equilibrium has to do with the concentration of your reactant in your products, but that's actually not the case. So this blue line right here, this is the rate of the reaction for creating NO2. And then this is the rate of the reaction for converting back to N2O4. So we can see here that right about at this mark, we get the same rate, right? It's that horizontal line. Our rates are equal. But our y-axis is our concentration. This is showing us that our concentration of NO2 is actually greater than N2O4, but the reason this is in equilibrium is because their rates are equivalent. The concentrations do not have to be the same. So if you're ever confused, just remember, for equilibrium to be a thing, my reverse and my forward reaction are at the same rate, but they don't have to have the same concentration. So I'll move this out of the way. So we can see here that we can make an equilibrium constant. So you might have learned how to kind of derive that, but I'm going to simplify it for you here. All you need to know is that KEQ is your equilibrium constant, and it's just a ratio of the rate of your forward reaction to your reverse reaction. KF and KR are just constants, right? It depends on which reaction you're doing. This means that my KEQ value is going to be different for every problem that I do. Okay, now let's kind of talk a little bit more about how to find this K value. So let's say we have an equation. We have two reactants and two products, right? And these little tiny values right here are our stoichiometric coefficients. So to calculate KEQ, which can also be represented as KC, that C right there is standing for concentration. That's what these brackets show, concentration. So what we're going to do is we're going to have products over reactants. So it's always going to be products over reactants in all of your equations, right? So we have our products. We have D and we have E over A and B. And we're going to raise them to the coefficient that's in front of them. So if this was 3 carbon dioxides, we would raise carbon dioxide to a 3. So that's kind of how this works. And let's move this back out of the way. Oh, I can't move it out of the way. That's okay. So we can also see that, there we go, our K equation can also represent pressure. So not only can we use it for concentration, but we can use it for pressure. So this would be the pressure of D raised to the coefficient, the pressure of E raised to the coefficient, and so on. And remember, it's always going to be products over reactants. So if you're ever confused, just make sure you're putting your products on top and then you're putting your reactants on the bottom. Now, so these are two ways in which we can show that KEQ value. And then there's actually this equation where we can convert between the two. So we know that the equilibrium constant for the pressure equals the equilibrium constant for the concentration times RT times change in N. And that change in N value has to do with moles. So we have our moles of our gaseous product minus the moles of your gaseous reactant. So what you have to do is you have to add up D and E and subtract that by A and B. So remember here, R is a constant, and then our T is our temperature. So stay tuned for the next lesson where we're going to give an example product with that.